Well, today we leave the wild, wacky, wonderful world of CPUs and turn our attention to GPUs. And don't worry, we're going to come back to CPUs too, but we're now adding one more trick to our bag of tricks. So let's talk about what makes a GPU a GPU. That's really what this note set is about. Okay, so history of GPUs. Before 1985, everyone had to do their 3D graphics all in software, and it was pig slow. Nobody would have ever thought to write a game that, well, people wrote Pong. That doesn't take much graphics power. Probably Pac-Man would have worked, but not the gaming that you know. But after 1985, vendors started producing graphics hardware cards. They plugged in and they took away a lot of the graphics capabilities that we did in software and implemented them in hardware, which made them super fast and let them run simultaneously. Because by putting in like more than one multiplication unit, you could process more than one vertex of, say, your jet fighter in your game. So around 1985 was that transition. And if you wanted to use the GPU, that's really all you could use it for, was doing graphics. Not that that was a bad thing. But people started to say, you know what, that's a lot of compute power bottled up in there. Is there some way we can get at it in order to do, say, scientific computing? And the answer was yes, but in a crude way. What people did is they reformatted their scientific applications to look like graphics applications and did that. So here's a fluid flow simulation, and every pixel is one particle in the fluid flow. The fragment shader is doing the physics equations for a fluid. Here's Conway's game of life, and every pixel is a participant in the game of life. Okay, that worked, but it was not really gratifying because everyone knew, why should you make your programming look like something else? Why not just make it look like programming? And so in the mid 2000 aughts, NVIDIA came out with CUDA, Compute Unified Device Architecture. The Kronos group came out with OpenCL, compute language. And that was C-like programming that put your stuff on a GPU and really used it like a GPU, but your interface was a C program, not faking it like this. Okay, now why do we care? Well, we care because GPUs are tailored to solve very specific problems. When you're playing a game and your 20,000 vertex jet fighter is screaming across the screen, well, every single one of those vertices is undergoing the same mathematical transformation. That's called data parallel. Okay, same equation, different data going into it. And so graphics hardware was designed with that idea in mind, data parallel. And so if you have a data parallel, say, scientific problem, GPUs are a pretty good choice. And so this is a graph of performance, and this was put together by NVIDIA. So it's somewhat self-serving, but the green line is performance. Here we are up in the 3 gigaflop range, and the blue lines are CPUs. But again, GPUs are really good at data parallel. If you're not doing data parallel, like you're following a linked list or a binary tree, GPU performance sucks. CPUs are meant to be general purpose, GPUs are not. Now, I took this graph and then they had other graphs, so I put that graph, the one from the previous page is this one, stretched out to match. If you follow this out, okay, so now we're into the late 2000 teens. And that difference is still going on. So here are CPUs down here, here are GPUs up here. And again, they are different architectures. Yeah, and now they're giving performance in AI inferences per second. And so, yeah, GPUs are just cranking right up there. This H10 with this H100, that's not even the most recent now. NVIDIA just announced the Blackwell, which is the B100, and so that's probably sitting up here somewhere. Okay, there are NVIDIA chips where you look at the spec sheet and it says we have 5,000 cores on our chip. And Intel says, oh, we have 16 cores on our chip. If you saw this on a scoreboard, you'd say, oh my gosh, what's going on? Well, what's going on is it's not an apples to apples comparison. Okay. So CPUs are general purpose. They have arithmetic logic units. Yes, they do. They also have control structures. They do process if statements, for loops. They traipse through linked lists, binary trees, and all of that. They also have cache because they're jumping all over memory. GPUs, well, they have cache, but much smaller. That they have a lot of arithmetic units because they don't have some of the other things. Okay, CPU chips will do branch prediction, they'll do out of order execution. That logic takes up chip space. Okay, GPUs don't do that. GPUs are really more streaming. Graphics, vertex comes in, or thousands of vertices come in, thousands of vertices get transformed by the same equation and go out. Okay, CPUs are meant to be general purpose. They do, well, whatever you ask them to do. So they're not as specialized as a GPU. Okay, at one time, this was what GPU architectures looked like. You know, oh, this little square here are the vertex shader processes. This square here are the pixel shader processes. That is, there were dedicated parts of the GPU to certain tasks. If you needed more pixel shader power, tough. This was the limit. But now architectures look more like this, where everything looks the same. And so if you need a part of the GPU to be a vertex shader, you just make it a vertex shader. And if you need more vertex shaders, you make more of these into vertex processors and maybe make more into pixel processors. So now it's a much more unified architecture that can be dynamically reconfigured to do certain things. And that plays perfectly into the idea of doing GPU computing. Okay, now let's take a look at this architecture. So this green set of blocks here, we go look at that and we see, well, there's an SM here in the corner, and that stands for streaming multiprocessor. That is actually a processor that does computing. Okay, and then these little green things are what NVIDIA calls CUDA cores. But the trick is they're not cores in the Intel sense. They don't have their own control logic and so on. They are, let's look over here, core. Oh, what is a core? It's a floating point unit and an integer unit combined. These things have no flow control of their own, no logic, no intelligence of their own. They take in numbers and do a certain arithmetic operation. And all of these are doing the exact same arithmetic operation. And that's really important. This works perfectly for graphics. It works great for data parallel programming, which we will do. Okay. And so, like in the end, NVIDIA 4090 chip, the 4090 chip has 128 streaming multiprocessors, which are sort of each one of these is one streaming multiprocessor. And then in each streaming multiprocessor, they have 128 CUDA cores, meaning they can be processing 128 chunks of numbers simultaneously with the same instruction, which means the chip has 16,000 of these CUDA cores on them. Okay, which is, wow, that's pretty cool. So, as we sort of look at all this, we realize that these are not really compute units. They are, I would call them an accelerator unit, maybe. They're a floating point accelerator. Sometimes the CPU vendors call these lanes, but again, understand that these are not full compute cores. They are arithmetic units, but you put enough of them together, all executing the same instructions on different data, and you've really got something. Now, I struggled with trying to come up with a physical analogy of this, and I found this. What is this? This is a grapefruit robot. Believe it or not, this is a grapefruit robot. It grabs grapefruits and lifts them up out of wherever it's grabbing them from and puts them in a carton. You know, 2 rows of 3 in the carton. Okay, these grippers have no intelligence of their own. They can't grope around looking for a grapefruit. When the robot says, "Open, you grippers," they all open. When it says, "Close, you grippers," they all close. Okay. And so in the GPU sense, the robot itself is like the streaming multiprocessor. The grippers are like the CUDA cores, and the grapefruit are like the data. Okay. The CUDA cores have no intelligence of their own. They do whatever the group instruction says, but on different data. So keep this in mind. We're going to beat this picture to death. Okay, if you look at spec sheets, yeah, here's our friend, the 4090 in the NVIDIA line. CUDA cores, 16,384. Look how much power it draws. Just the card, just the card. It draws 850 watts. Typically, you need like 2 to 300 watts just to run the PC. But now you have to add another 4 to 5 times that just to run the graphics card. That's how things work these days. Okay, and then there's others. That's sort of what the different entries are in the product line is different numbers of CUDA cores, different amount of power being drawn. The width of the memory interface is different. I think they're up to 512 now. Maybe in Blackwell they're up to 512. Anyway, this is the kind of spec sheet that you will often see. Like, if you turn your head sideways, this has got some others too. I love this one because it's got billions of transistors on it. So here's 32 billion transistors, 46 billion transistors. So that's pretty cool. Tom's Hardware puts out charts like this. If you don't subscribe to Tom's Hardware, you probably should. This is what the NVIDIA Ampere chip looks like. These are the streaming multiprocessors and their CUDA cores in here. So yes, lots of cool stuff going on. All right, bottom line, CPUs and GPUs have different target applications. If you're traipsing through a binary tree, that's a horrible use for a GPU. Shouldn't even try it. But CPUs, yeah. But if you're doing data parallel, GPUs are the best game in town. Again, we're going to use this. Okay. Streaming multiprocessor is what NVIDIA calls it. Everyone else calls that same thing a compute unit. CUDA core is what NVIDIA calls it. Everyone else calls it a processing element. Unfortunately, you'll hear me go back and forth, but just know that they're the same thing. Okay, so graphics cards contain a certain number of compute units. They're arranged in a grid. Each compute unit takes a certain number of processing elements, again, arranged in a grid. And so, yeah, compute units are streaming multiprocessors, processing elements, these guys, they are the CUDA cores. All right, how do we write C code for this? Well, first of all, don't do it if it's a bad application. If it's not intensely data parallel, don't use a GPU. It's just not worth it. But if it's data parallel, lots of pieces of data, same arithmetic operation, great. GPUs are wonderful. GPU programs are expected to not just have a couple of threads running these different data values. They expect you to have thousands of them. Again, that's a good use for a GPU. If all you've got is 16 chunks of data that you want to process, don't use a GPU. The overhead of creating the GPU setup will dwarf the savings and performance you were hoping to get. Each thread executes the same program, that's called the kernel, but on different data. You have many, many, many threads. They all wake up at the same time. They all are told, here's your instruction to do, and here's your data to do it on. We're going to do one project in CUDA, one project in OpenCL, so that you get to see both. And even if you've got 128, say, CUDA cores per streaming multiprocessor, typically we always put in more pieces of data than we can handle at a time. And the reason is if one of those chunks of data gets blocked, like it has to wait to get values out of memory, well, the GPU is just going to bring in another block of 128 and let that run. And so typically we ask for more per streaming multiprocessor than just the number of CUDA cores. Yep, break your problem into small pieces. This is one of my former students did this really great GPU-based particle system that ended up getting a performance of like 1 billion particles per second. All right, new thing in GPUs, which we're not going to talk about, but I'd like you to see the term, is tensor core. Okay, tensor cores are used to solve sort of matrix, 3D matrix type operations. And they're really, really prevalent in machine learning, which is why they're so hot today. Okay. They do this sort of thing. You know, they'll take a 4x4 times a 4x4 and add in another 4x4. And so if you see tensor cores on one of your GPU chips, you know that's what this will do. The other interesting thing about those tensor cores is they do something called fused multiply add. So if you have something in this form, D equals A plus the quantity B times C, normally you would think the compiler would translate it like this. Let's multiply B times C and let's add A and put it in D. But this fused multiply add does it at the same time. Now, how does that work? Well, let's work a problem. 123 times 456, adding 789. So notice that if we set up this multiply, 6 times 3 is 18, carry the 1, but the moment that 8 appears, we can start the addition. Oh, 8 plus 9 is 7. And by that time, maybe the multiply has produced the next number. And we'll so add there. And maybe by that time, the multiplies produce the next number. This is what fused multiply add means, is you are not doing one finishing, then doing the other. It means the add is starting before the multiply is finished. And that makes this look even faster. And CPUs have started adding this capability as well. Okay, and again, just for the sake of completeness, there's also something called ray trace cores on the newer GPU. This is not a graphics course. We're not going to talk about that. But if you want to see what that lets you do, click on that link. It's pretty cool. All right, the rest of this, well, here we're talking about CUDA versus OpenCL. It has to do with how it works with the compiler. For CUDA, they made everything goes in one file, and a special compiler handles the GPU code and it also handles the CPU code. For OpenCL, they put everything in two files. One file is the GPU code, one file is the CPU code. You'll get to do both. So you'll get to understand the advantages of each. There are some advantages of putting everything in one file like CUDA does. There are some advantages of putting everything in two files like OpenCL does. So stay tuned with that. Okay. If a bunch of the grippers are executing the same program at the same time, what happens with if statements? Well, that is one of the banes of GPUs, but the way they handle it is they put together a group of ones and zeros based on how each gripper, how each CUDA core evaluates this if statement. Then the GPU actually executes both halves of the if statement, but it only allows things to get stored based on this array of ones and zeros that the if statement produced. Okay, in general, you would love to minimize the number of if statements you have in GPU code. Okay, so here's the takeaway. GPUs stream data. That's what computer graphics does. That's how they were designed, but now you can apply them to data parallel computing. All right, the rest of this is disassembling a graphics card, which I just happen to have right here in my office. This is one that died, and I grabbed it before anybody could throw it out. But yeah, if you've ever wondered what the inside of a graphics card looks like, well, it looks like that. There's the heat sink. And it looks like that. Here's the heat sink. Here's the underside of the heat sink. And right under this big piece of metal is the GPU chip. So that big chunky square of metal, its job is to funnel heat off the GPU chip to get up to the cooling fins. Here's the GPU card. There's the chip. These little chips around it are all memory. This part over here is video out. You can see the video connections here. And this part over here, surprisingly, is all power. This is power in. There's the power cable connectors, capacitors to smooth it out, voltage regulators here. That whole, like 1/3 of the board is just dedicated to getting clean power to the chip, like that. And there's a close up here. This one only had 72 billion transistors. This is the underside of the card. There's other chips and things soldered there. These are all the pins. So here are pins from the chip. Out here are pins from the GPU chip. Anyway, this is what this looks like. If you've never seen one, and I recommend you not take your own apart. In this video, somebody actually took a working card apart and put it back together and plugged it back in, and it still worked. Very gutsy. I don't recommend you do that. All right, so welcome to the world of GPUs. This is going to be a real adventure as we start now to apply this to parallel computing.